Hello, I'm Alex. The universe lied to us. 13.8 billion years wrong. Scientists just found 6 red dots that broke everything. Tonight, you'll learn what really came before the Big Bang. Get comfortable. This changes everything. Let's begin. You know that feeling when you open your grandparents' old diary and discover they had an iPhone before landline telephones were even invented? That moment when your brain stutters, trying to make sense of something that simply cannot be true. That's exactly how astronomers felt on a cold December morning in 2021. Except what they found wasn't in a diary. It was written in light that had traveled for over 13 billion years to reach us. 13.8 billion years. That number has been carved into every textbook, embedded in every documentary, accepted as the unshakable foundation of cosmic history, the age of everything, the moment when time itself began, when nothing became something, when darkness exploded into light. December 2021 changed everything. A machine the size of a tennis court unfolded in the darkness of space 1 million miles from Earth. The James Webb Space Telescope hung there in the void, suspended at a gravitational balance point where the pull of Earth and Sun cancel each other out. It was alone, silent, perfect. Engineers had spent decades designing it. Gold-coated mirrors arranged in a hexagonal flower, each panel polished to within a fraction of a wavelength. Instruments cooled to nearly absolute zero, so cold that heat from the telescope itself wouldn't blind its vision. And a sun shield, 5 layers of material thinner than a human hair, stretched across an area larger than a tennis court to block the sun's overwhelming glare. This wasn't just another telescope. This was a time machine. Because when you look far enough into space, you're looking back in time. Light travels fast, but the universe is vast. The light reaching your eyes, right now from distant galaxies, was emitted when the universe was young, when the first stars flickered to life, when darkness finally broke after hundreds of millions of years of cosmic night. Scientists pointed Webb toward a patch of sky near the Big Dipper. Hubble had looked there before and seen nothing particularly special, but Webb sees an infrared catching light that has been stretched across billions of years of cosmic expansion. Light so old it has shifted from visible blue and green into invisible infrared. Light from the very edge of everything we can see. Within days of releasing its first deep field images, researchers spotted something wrong. 6 bright red dots appeared in the data. At first glance, they looked like distant quasars, maybe dust, possibly measurement errors. Then the team measured their redshift, that telltale signature of how far light has traveled through expanding space. They ran the numbers through their equations, checking and rechecking, because the results seemed impossible. The numbers came back insane. These objects existed just 500 to 700 million years after the universe began. In cosmic terms, that's infancy. The Big Bang happened. Space expanded. Matter cooled. And somehow impossibly, these massive structures had already assembled themselves. Here's why that shattered everything. According to every model we have, early galaxies should be small. Tiny dwarf systems containing maybe 100 million stars slowly pulling together under gravity's patient hand. These are the cosmic toddlers stumbling into existence, figuring out how to exist at all. These 6 objects contained tens of billions of stars each. Let that sink in for a moment. Tens of billions. Some appeared nearly as massive as our modern Milky Way, which took over 13 billion years to build through countless mergers and collisions. These ancient giants somehow existed when the universe was less than 5% of its current age. A researcher from the University of Colorado Boulder put it plainly. Her words carried the weight of someone watching their entire field's foundation crack. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. The mathematics of galaxy formation are brutal. Stars don't just appear out of nothing. Gas must cool collapse, under gravity reach temperatures and pressures high enough to ignite nuclear fusion. That takes time. Lots of it. Our Milky Way births maybe 2 new stars per year. It's leisurely, patient, for these ancient galaxies to reach their observed size. In just 700 million years, they would need to create hundreds of stars annually for hundreds of millions of years straight, without stopping, without the breaks that feedback from supernovae and stellar winds should cause. Even then, the numbers barely work. Add another problem. The early universe lacked heavy elements. The first stars formed from pure hydrogen and helium, the only elements created in the Big Bang itself. Everything heavier, every atom of carbon, oxygen, iron, had to be forged inside stars and scattered by supernova. Heavier matter makes large galaxy formation easier. It allows gas to cool faster, collapse more efficiently. These objects somehow bypassed all the rules. More data made things stranger. Some of these early galaxies appeared smaller in physical size, despite containing more mass than larger neighbors. That's backwards. That violates everything we know about how structures grow in the universe. In cosmic evolution, more mass accumulates in bigger systems over time. You don't get dwarf galaxies with Milky Way masses. It doesn't work that way. These did exactly that. Scientists started using phrases like impossibly dense and physically inexplicable. These weren't exaggerations. These were admissions that something fundamental was broken, either in the galaxies themselves or in our understanding of time. And tonight, when you lay down to sleep, try to imagine that someone has just found evidence that everything you know about time itself might be wrong. The discovery triggered what scientists diplomatically call the impossible early galaxy problem. It's not just one weird object that might be a fluke. Webb kept finding them. Dozens of massive mature galaxies existing when the cosmic timeline says they shouldn't. Some showed disk structures and central bulges, typically associated with billions of years of evolution. Others displayed organized spiral patterns like miniature versions of galaxies we see in the local universe today. These weren't chaotic clouds of newborn stars stumbling into existence. They looked grown up, established, ancient in appearance. Despite being cosmically young, every new observation deepened the mystery. Scientists around the world scrambled to explain it. Maybe black holes at these galaxies' cores produce extra light, making them appear more massive than they truly are. Recent research suggests this might account for some cases. The light we interpret as starlight could partly be radiation from gas swirling into supermassive black holes at millions of degrees, shining brighter than billions of suns. That would reduce the estimated stellar mass. But even cutting the numbers in half leaves galaxies far too large for their age. Another proposal suggests stars formed faster in the early universe, Because it was denser. In a denser environment, gravity is stronger. Gas has a harder time escaping when massive stars explode. Maybe early galaxies could hold on to their gas better, allowing for higher star formation efficiency. Possible, but the effect would need to be extreme to match observations, and computer simulations show it's not extreme enough. What nobody expected was the simplest explanation. What if the galaxies aren't too big? What if the universe is too young? Scientists actually use the word bananas to describe this discovery, not because they were hungry, but because their brains were refusing to accept what their eyes were seeing. What if our most fundamental assumption about cosmic age is wrong by a factor of 2? The James Webb revelations didn't just show us distant galaxies. They showed us a universe that doesn't fit inside 13.8 billion years. Something has to give. Either the physics of star formation is completely alien in the early cosmos, operating under rules we don't understand, or time itself is longer than we thought, much longer. But these 6 red dots were just the beginning of a much bigger unraveling. The problem isn't just that these galaxies are big. The problem is they're impossibly efficient at something the universe shouldn't know how to do yet. Let's talk about how galaxies actually form, because understanding what should happen makes what we're seeing even more disturbing. Our Milky Way is a beautiful spiral galaxy containing somewhere between 2 and 400 billion stars. It has a disk spiral, arms, a central bulge, a supermassive black hole at its core. It's organized, mature, elegant. It took 13 billion years to build. The Milky Way didn't just appear one day fully formed. It assembled through hundreds, possibly thousands of mergers with smaller galaxies over cosmic time. Each merger was violent, chaotic, taking hundreds of millions of years to settle down. Stars formed in bursts during collisions. Then star formation would pause while the system reorganized itself. Currently, our galaxy births about 2 new stars per year. That's pretty typical for a mature galaxy. Some years more, some years less, but 2 is the average. It's a leisurely pace. There's no rush. The universe has been around for 13.8 billion years. What's the hurry? Now, consider what these ancient galaxies had to do. They existed just 700 million years after the Big Bang. To reach their observed masses, they needed to create hundreds of billions of stars in that time. Let's be conservative and say 50 billion stars. That requires creating over 70 stars per year, every single year, for 700 million years straight. That's 35 times the Milky Way's current rate, for 700 million years. Without stopping, the mathematics gets worse when you consider feedback processes. When massive stars form, they don't just sit there politely shining. They blast intense radiation into surrounding gas, heating it to millions of degrees. When they die, just a few million years later, they explode as supernovae, creating shock waves that blow gas clear out of the galaxy entirely. This feedback is self-regulating. It prevents galaxies from forming stars too quickly. It's like a thermostat. Star formation heats things up, which shuts star formation down, which lets things cool, which allows star formation to resume. The cycle repeats, but it's slow and inefficient. Only about 20% of available gas in a typical galaxy actually becomes stars. The rest gets heated, blown away, or locked up in forms that can't collapse. Then, Webb found what researchers started calling the red monsters. 3 galaxies, existing within the first billion years, each appearing nearly as massive as our modern Milky Way. When scientists calculated their star formation efficiency, the numbers came back shocking. These systems appeared to be converting 40 to 60% of their available gas into stars. That's 3 times more efficient than any galaxy should be. The lead researcher stated plainly that this efficiency reshapes our understanding of galaxy formation in the early universe. That scientists speak for, we have no idea how this is possible. It's like meeting a 3-year-old child who already has a PhD, runs a Fortune 500 company, and is planning retirement. You wouldn't think, wow, gifted kid. You'd think, something is seriously wrong with this birthday calendar. More problems emerged. Some of these early galaxies packed enormous stellar masses into surprisingly compact volumes. They appeared smaller than expected, given their mass, denser. One might think that just means they're compressed, but density creates its own issues. Gravity in such concentrated systems should trigger rapid bursts of star formation and black hole growth. The galaxies should burn through their gas supplies quickly and shut down. Instead, they appear to be thriving, actively forming stars, showing no signs of the quenching process that stops star formation in dense environments. It's as if the physics of gravity operates differently in the early universe. Scientists proposed dozens of explanations. Maybe the initial mass function was different in early galaxies. That's the distribution of star sizes when they form. In nearby galaxies, most stars are small, around half the sun's mass or less. Massive stars are rare. If early galaxies produce more massive stars, they would look brighter and more massive than they actually are. Massive stars shine intensely during their brief lives. A galaxy filled with them could appear to contain more stellar mass than it really does. Testing this requires detailed spectroscopic observations. Webb's instruments can do this, but the analysis takes time and careful work. Early results are mixed. Some massive early galaxies show spectral features consistent with normal stellar populations. Others display unusual emission lines that could indicate different star formation processes. But even invoking unusual stellar populations doesn't fully solve the problem. Another idea suggests that supermassive black holes at these galaxies' centers contributed significant light. Gas, spiraling into black holes, emits intense radiation before crossing the event horizon. This could make galaxies appear brighter and more massive than their stellar content alone would suggest. Recent observations support this in some cases, but not all. Many of the massive early galaxies show no signs of active black hole feeding. The light appears to genuinely come from stars. The simplest explanation remains the most unsettling. These galaxies aren't too big for their ages. They're exactly the right size for the amount of time they've actually existed. But that time isn't 700 million years. It's much longer. If the universe is actually 26 billion years old, instead of 13.8, these galaxies had over 1 billion years to form, instead of half that. Suddenly, the impossible becomes merely difficult. The timeline pressure eases. Star formation rates don't need to be absurdly high. Efficiency doesn't need to violate physics. Feedback processes can operate normally. The galaxies just had more time. And maybe you're wondering right now, why should I care about some distant red dots? Because those red dots are whispering that everything you learned about origins might be an unfinished story. This realization spread through the astronomical community like a slow wildfire. Papers began hedging their language. Instead of declaring the galaxies impossible, researchers described them as challenging or unexpected. The shift was subtle, but significant. Scientists were entertaining the possibility that the James Webb discoveries weren't revealing exotic early universe physics. They were revealing that our cosmic clock was miscalibrated. The universe wasn't breaking physics. It was breaking our assumptions about its age. And if those assumptions were wrong, we'd need to reconsider everything, including the stars that refuse to die. 200 light years from Earth, in the constellation, Libra floats a star that shouldn't exist. It has a catalog designation HD 140283, but astronomers call it Methuselah, after the biblical figure who supposedly lived 969 years. The nickname is fitting, though even that ancient patriarch looks like an infant compared to this stellar elder. This star races across the sky at 800,000 miles per hour. That's not normal stellar motion. Most stars in our neighborhood drift slowly following stable orbits around the galactic center. Methuselah tears through space like a refugee fleeing some cosmic catastrophe. Its trajectory and velocity suggest it formed elsewhere and was flung into our region billions of years ago, possibly when a dwarf galaxy was torn apart by the Milky Way's gravity. But speed isn't what makes this star remarkable. What makes it remarkable is what it's made of, or rather, what it's not made of. When astronomers analyzed its light through spectroscopy, breaking starlight into its component wavelengths to see what elements it contains, they found something shocking. Methuselah contains barely any elements heavier than hydrogen and helium. Its metallicity, the term astronomers use for anything heavier than helium, is 1/250th that of our Sun. That's not just old, that's primordial. The early universe produced only hydrogen helium and trace amounts of lithium in the Big Bang's first minutes. Everything else, every atom of carbon that makes up your body, every oxygen molecule you breathe, every iron atom in your blood, had to be forged inside stars and scattered across space by supernovae. The first generation of stars, called Population 3, formed from pure primordial gas with essentially zero metals. They lived fast, burned bright, and died young in spectacular explosions that seeded space with heavier elements for the first time. The second generation, Population 2 stars, formed from gas enriched by those first supernovae. They have low metallicity, but not zero. They're ancient, but not the first. Methuselah is a Population 2 star. It formed after the first stars died, but before much metal had accumulated in the universe. That places its birth extremely early in cosmic history. Measuring a star's age requires understanding its internal physics. Stars spend most of their lives on what astronomers call the main sequence, burning hydrogen into helium in their cores through nuclear fusion. This phase lasts billions of years for stars like our Sun. Eventually, the hydrogen fuel runs out, the core contracts and heats up. The outer layers expand dramatically. The star becomes a red giant swelling to hundreds of times its original size. How long this takes depends on the star's mass, its initial composition, and the details of how heat and elements move through its interior. By measuring a star's current brightness, temperature, and chemical composition, then modeling its evolution backward through time, astronomers can estimate when it formed. Methuselah has already left the main sequence. It's a subgiant just beginning its expansion toward the red giant phase. By running the stellar evolution models, astronomers can calculate how long it's been burning. The first serious age estimate came from observations with the Hipparcos satellite in 2000. The result created an instant crisis, 16 billion years old. That's older than any reasonable estimate of the universe's age at the time. The mathematics screamed impossible. Either the star's age was catastrophically wrong, or the universe's age was wrong, or our understanding of how stars evolve was fundamentally broken. There was no fourth option. Scientists scrambled to refine the measurements. In 2013, the Hubble Space Telescope's fine guidance sensors measured Methuselah's distance with 5 times better precision than Hipparcos. Better distance measurement leads to better estimates of the star's true brightness, which directly affects age calculations. The new result, 14.5 billion years, plus or minus 800 million years. That uncertainty range became crucial. The lower bound of the estimate, 13.7 billion years, technically overlapped with the universe's calculated age. Scientists emphasized this overlap heavily in public communications. Within the error bars, they argued everything was consistent. There was no real paradox. But privately, many felt deeply uncomfortable. The central estimate, the most likely age, still exceeded cosmic time. And there was something suspicious about how the error bars kept getting adjusted to barely include the universe's age. It felt like forcing a solution rather than finding one. Scientists kept adjusting those error bars, like someone trying to squeeze into old jeans. Technically, it fits, but everyone can see it's not comfortable. More recent studies in 2021 and 2022 revised the age again this time, using interferometric observations and more sophisticated stellar models that account for things like element diffusion and magnetic fields. The new estimates ranged from 12 to 14 billion years, depending on which parameters you assume. The paradox seemed resolved. Methuselah's age now comfortably fit within cosmic time. Crisis averted. Except it wasn't really resolved. It just got hidden inside larger uncertainty ranges, and Methuselah isn't alone. Globular clusters scattered around the Milky Way's halo contain thousands of similarly ancient stars. These dense spheres of stars orbit the galaxy like cosmic fossils, preserving information about conditions when the galaxy was young. All the stars in a cluster formed around the same time, from the same gas cloud, making them perfect laboratories for measuring ages. Many globular clusters show ages of 12 to 13.5 billion years. Some estimates push even higher, given that the universe is supposedly 13.8 billion years old. This leaves only a few hundred million years for the Big Bang to occur, the universe to cool the first stars, to ignite those first stars, to die and enrich space with metals and globular clusters to form from that enriched material. The timeline is crushingly tight. Methuselah is just the closest, best studied example of a widespread problem. It's the poster child because it's near enough to study in detail and clear enough that we can't dismiss the measurements as errors. There are other candidates, even more suspicious. A star in the constellation Aquarius has an estimated age of 14.8 billion years, but it's farther away, harder to study, precisely easier to wave away as measurement uncertainty. Methuselah was chosen for intense scrutiny because it's close enough to verify and clear enough that we cannot deny what we're seeing. Tonight, when you look up at the sky, remember that there are stars out there that existed before the beginning, and they're waiting for us to admit the truth. But to understand how we got this timeline wrong, we need to go back to the man who first discovered the universe was expanding. For nearly a century, scientists have been trying to answer one question: how old is everything? The number we arrived at, 13.8 billion years, didn't come from guessing. It came from measuring the universe's expansion rate, observing the oldest stars, and analyzing radiation left over from the Big Bang itself. This age became cosmology's bedrock. Every textbook accepts it. Every model of cosmic evolution builds from it. But the path to this number was messier than most people realize, and the cracks in its foundation have been there from the start. The story begins in the 1920s with Edwin Hubble working at Mount Wilson Observatory. With the most powerful telescope of his era, Hubble measured light from distant galaxies. He noticed something shocking. The light was redshifted, stretched toward longer wavelengths, and the farther the galaxy, the more its light shifted. This wasn't random scatter. It followed a pattern. More distant galaxies moved away faster. Their light stretched more by the expansion of space itself. Hubble realized the universe wasn't static, frozen in eternal unchanging equilibrium, as everyone assumed. It was growing, expanding, and if you run that expansion backward, in time rewinding the cosmic movie, everything must have been closer together in the past. Keep rewinding far enough, and everything converges to a single point. That point became known as the Big Bang. But knowing the universe is expanding doesn't immediately tell you its age. You need to measure how fast it's expanding. That rate is called the Hubble constant, named after the man who discovered it. Measuring it accurately turned into one of astronomy's biggest headaches. Early estimates varied wildly. When the Hubble Space Telescope launched in the 1990s, scientists thought the universe might be anywhere from 7 to 20 billion years old. That's an uncertainty range larger than the age of Earth itself. The problem was measuring cosmic distances accurately. A small error in distance translates to a huge error in age. By the early 2000s, new techniques narrowed the range. Scientists used observations of type Ia supernovae exploding stars that shine with remarkably consistent brightness. These cosmic lighthouses become standard candles for measuring distances. If you know how bright something actually is and measure how bright it appears, you can calculate how far away it must be by observing thousands of supernovae Across cosmic history, astronomers refined the expansion rate with increasing precision. Another breakthrough came from studying the cosmic microwave background, that faint radiation left over from when the universe was only 380,000 years old. Space was opaque before that moment, filled with a hot plasma that scattered light in every direction. When the universe cooled enough for atoms to form, photons could travel freely for the first time. The European Planck satellite mapped this ancient radiation with incredible precision from 2009 to 2013. The resulting data revealed tiny temperature fluctuations that encode information about the universe's age, composition, geometry, and fate. All the methods converged on the same answer: 13.797 billion years, plus or minus 23 million years. That's an uncertainty of less than 1%. It seemed like cosmology had finally nailed down its most important number. The lambda CDM model, our standard picture of cosmic evolution, incorporated this age. It explained how matter clumped into galaxies, how the cosmic microwave background formed how light elements were created in the Big Bang's first minutes. Everything fit together into an elegant story. But even as this consensus formed, troubling observations accumulated. Some measurements of the Hubble constant using nearby galaxies suggested a faster expansion rate than the cosmic microwave background predicted. Different methods gave different answers. Measurements from relatively nearby supernovae and pulsating variable stars, called Cepheids, consistently yielded values around 73 kilometers per second per megaparsec. That means a galaxy 1 megaparsec away, about 3.2 million light years, recedes at 73 kilometers per second due to cosmic expansion. But measurements derived from the cosmic microwave background gave values around 67 kilometers per second per megaparsec. Slower expansion, older universe. The disagreement is about 10%. That might not sound like much, but in cosmology, it's enormous. This became known as the Hubble tension, a growing disagreement between different measurement methods that refuses to go away despite years of scrutiny. It's like using two different rulers to measure your child's height. One says 1 meter 20 centimeters. The other says 1 meter 35. You don't think my child is strange. You think one of these rulers is broken. This isn't measurement error. Both methods appear robust. As techniques improve and more data accumulates, the disagreement becomes more statistically significant rather than resolving. Either something is systematically wrong with one method, or there's new physics operating that our standard model doesn't capture. The faster expansion rate implies a younger universe somewhere between 11 and 12 billion years, depending on exact assumptions. The slower rate from the cosmic microwave background implies the older 13.8 billion year age. They can't both be right, and this is where our story starts to become stranger than science fiction, because sometimes the truth is more insane than imagination. The Hubble tension suggests that our ruler for measuring cosmic time might be fundamentally miscalibrated, not by a little bit, by billions of years. But the tension between numbers was just the beginning. The real crisis came when we started finding things that shouldn't exist. Let's step back for a moment and look at what we've gathered so far, because when you lay all the evidence out together, the pattern becomes impossible to ignore. First, the James Webb Space Telescope discovers massive galaxies that shouldn't exist. 6 bright red dots containing tens of billions of stars, each existing just 5 to 700 million years after the Big Bang. They're too large to mature, too organized for their supposed age. The mathematics of galaxy formation says they didn't have enough time, yet there they are, shining in infrared light that has traveled over 13 billion years to reach us, second Methuselah and other ancient stars. Population 2, stars with ages that push uncomfortably close to or even exceed the universe's calculated age. Globular clusters filled with stars 12 to 13.5 billion years old. These measurements come from multiple independent methods. They're not flukes. They're not errors we can wave away. The stars are telling us they're older than they should be. Third, the Hubble tension. 2 different ways of measuring cosmic expansion give 2 different answers. Nearby observations suggest the universe is younger, around 11 to 12 billion years. The cosmic microwave background suggests it's older 13.8 billion years. The disagreement is statistically significant and growing more pronounced as measurements improve. One of our rulers is broken. Fourth, the globular cluster timeline problem. If the universe is 13.8 billion years old, and globular clusters are 12 to 13.5 billion years old, that leaves only 3 to 800 million years after the Big Bang for everything else to happen. The universe needs to cool. The first stars need to form from primordial hydrogen and helium. Those stars need to live their lives and die as supernovae, scattering heavier elements into space. Gas clouds, enriched with those elements, need to collapse and form the second generation of stars that make up globular clusters. 3 to 800 million years for all of that. It's possible, barely, but it requires everything to happen with perfect efficiency. No delays, no wasted time. Every process operating at its theoretical maximum speed. Fifth metal enrichment history. The universe started with only hydrogen, helium, and trace lithium. Everything heavier had to be created inside stars. This chemical enrichment takes time. Multiple generations of stars need to form fuse elements in their cores and explode to distribute those elements. The observed metal content in ancient stars suggests this enrichment process was already well underway within the first billion years. That requires not just one generation of stars, but multiple generations forming and dying in rapid succession. The timeline is strained, stressed, barely holding together. Each of these problems individually might be explainable. Maybe we don't fully understand star formation in the early universe. Maybe stellar evolution models need refinement. Maybe there's some exotic physics we haven't discovered yet that operated in the cosmic dawn. But when you stack them all together, when every independent line of evidence points in the same direction, a pattern emerges. The pattern screams, there isn't enough time. We're left with 2 possibilities. The first option, physics in the early universe, was completely different. Exotic, alien. Stars formed faster. Galaxies assembled through mechanisms we don't understand. Fundamental constants might have been different. The rules themselves might have changed. This is possible. The early universe was a strange place. Temperatures were higher. Densities were higher. Conditions we can never reproduce in laboratories. Maybe in that alien environment things worked differently, but invoking exotic physics is expensive in science. It requires adding new assumptions, new mechanisms, new processes that we have no independent evidence for. It's like explaining why your car won't start by proposing that the laws of combustion are different in your driveway. Maybe that's true, but it's more likely that something mundane is wrong. The second option is simpler and somehow more shocking. What if the galaxies aren't too big? What if the stars aren't too old? What if the metal enrichment isn't too fast? What if all these observations are perfectly normal for the amount of time that's actually passed? What if the timeline itself is wrong? A physicist once described the current situation like this: we're like blind people touching an elephant. Each person touches one part and tells a different story. But if all of us are saying, this elephant is too big for this box, then maybe the problem isn't the elephant. Maybe it's the box. The box, in this case, is 13.8 billion years. And everything we're observing is telling us that box is too small. Consider what happens if you simply double the timeline. Give the universe not 13.8 billion years, but 26 or 27 billion years. Suddenly, everything that seemed impossible becomes merely difficult. Those massive early galaxies, they had over 1 billion years to form instead of half that. Star formation rates don't need to be absurdly high. They just need to be normal, sustained over longer periods. Methuselah and the ancient stars. A 14 billion year old star isn't older than a 26 billion year old universe. It's just an ancient star that formed relatively early, perhaps 5 or 6 billion years after the actual beginning. No paradox, no uncomfortable error bar manipulation. The Hubble tension. With a longer timeline, there's more room for expansion rates to vary in ways that reconcile different measurements. The disagreement doesn't disappear, but it becomes less acute. Globular clusters. Instead of forming just a few 100 million years after the Big Bang, they formed 2 or 3 billion years after the beginning. That's plenty of time for the first generation of stars to live and die, for space to be enriched with metals, for the second generation to coalesce into dense clusters. Metal enrichment. Multiple stellar generations can occur naturally without requiring absurd efficiency. The chemical evolution of the universe proceeds at a normal, physically reasonable pace. One change, double the age, and 5 separate problems all ease simultaneously. That's not coincidence. That's evidence. But accepting this means questioning one of cosmology's most fundamental conclusions. It means admitting that our measurements of cosmic age, refined over decades by thousands of scientists using multiple independent methods, might be systematically wrong by a factor of 2. That's a radical claim. Revolutionary claims require revolutionary evidence. And for years, there wasn't a clear theoretical framework for how the universe could be twice as old, while still explaining all the observations that led us to 13.8 billion years in the first place. Then, in July of 2023, a paper appeared that changed everything. The author was a man named Rajendra Gupta, working at the University of Ottawa in Canada. He's not a celebrity scientist. He doesn't have a Nobel Prize. He's an adjunct professor teaching and researching without the massive research grants and teams that famous cosmologists command. But he had an idea, a simple idea that combined two old, supposedly dead theories in a way that nobody had seriously considered before. And when he ran the mathematics through actual observational data, something remarkable happened. Everything fit. The impossible early galaxies stopped being impossible. The ancient stars stopped being paradoxes. The tensions eased, and the universe aged from 13.8 billion years to 26.7 billion years. Before we meet him and understand what he discovered, try to imagine something. If someone told you that you'd actually lived twice as long as you thought, how would that change your understanding of your life? Every memory would suddenly have more context. Every experience would fit into a longer story. Things that seemed rushed and inexplicable would make sense if you just had more time. That's exactly what's about to happen to our universe. And the man who made it possible didn't use new observations or better telescopes. He used something far more surprising ideas that science had buried 50 years ago. July 2023. A paper appeared in the monthly notices of the Royal Astronomical Society, one of the most respected journals in astronomy. The title was Technical Dense with Physics Terminology. Most people scrolling through the journal that month probably skipped right past it. The author was Rajendra Gupta, a physicist at the University of Ottawa in Canada. He's not a household name. He doesn't have a Nobel Prize sitting on his desk. He's not the kind of scientist who appears in documentaries with dramatic lighting and sweeping orchestral music. He's an adjunct professor, teaching classes, conducting research, doing the quiet work that most scientists do far from the spotlight. But in this paper, he said something extraordinarily simple, something so straightforward that it sounded almost naive. What if the universe is 26.7 billion years old? Not 13.8 billion, not 14 or 15 billion, as some of the Hubble tension measurements suggested. 26.7 billion years, nearly double the age carved into every textbook, nearly double what every cosmology course teaches, nearly double what decades of careful measurement had supposedly confirmed. The reaction from the scientific community was immediate and divided. Some researchers found it intriguing, worth investigating. The paper was published in a respected journal after all. The mathematics appeared sound. The approach was novel. Maybe this adjunct professor in Canada had noticed something everyone else had missed. Others dismissed it immediately. This is crazy, impossible. It contradicts too many established observations. The standard model of cosmology, lambda CDM, had been tested and refined for decades. It fit most observations remarkably well. Throwing it out based on one paper seemed reckless. But nobody could deny one crucial fact: Gupta's model solved all the problems simultaneously. The massive early galaxies from James Webb explained. They had more time to form. Methuselah and the ancient stars explained. They weren't older than the universe anymore. The Hubble tension eased. The extended timeline provided room for different expansion rates to be reconciled. Globular clusters explained. They formed billions of years after the Big Bang, not hundreds of millions, giving plenty of time for stellar generations to cycle. Metal enrichment explained. Chemical evolution proceeded at a normal, physically reasonable pace, one change, one bold claim, and 5 separate crises all dissolved. That's the hallmark of a good theory. It doesn't just solve one problem by creating 5 others. It solves multiple problems with a single, elegant adjustment. Occam's razor favors simplicity, and despite how radical it sounds, doubling the universe's age is actually simpler than inventing exotic physics for the early cosmos. Gupta's approach wasn't a random guess. It wasn't pulling numbers out of thin air. He combined 2 old ideas that mainstream cosmology had abandoned decades ago. Ideas that were supposedly dead-buried, relegated to the footnotes of physics history. The first was tired light theory, originally proposed by Fritz Zwicky in 1929. The second was evolving coupling constants, suggested by Paul Dirac in 1937. Separately, both ideas had been tested and rejected. They didn't fit observations. They created more problems than they solved. But Gupta didn't use them separately. He combined them in a hybrid framework, carefully balancing their contributions so that each compensated for the other's weaknesses. Then, he applied this framework to actual observational data from supernovae and the cosmic microwave background. The result? A surprisingly good fit. Not perfect. Science is never perfect, but good enough that it couldn't be dismissed as obvious nonsense. The model explained the James Webb discoveries without requiring absurd star formation rates or exotic galaxy assembly mechanisms. It explained ancient stellar ages without uncomfortable error bar manipulation. It provided a pathway toward resolving the Hubble tension. Most scientists, when they first read this paper, had expressions similar to what you'd have if your crush told you they already have a crush on someone else. Shock, disbelief, an instinct to reject the information. But deep down, somewhere in the back of your mind, a tiny voice whispering that maybe, just maybe, it actually makes sense. Because here's the thing about revolutionary ideas in science. They always sound crazy at first. Continental drift was mocked for decades before becoming plate tectonics, the foundation of geology. The Big Bang itself was considered absurd when first proposed. Einstein called it his biggest blunder. Atoms were philosophical speculation for centuries before becoming experimentally confirmed. We have a pattern in science of rejecting ideas that challenge our fundamental assumptions, then grudgingly accepting them when evidence becomes overwhelming. The question is whether Gupta's older universe will follow that pattern or fade into obscurity. As another interesting idea that didn't pan out, the evidence is starting to accumulate. In 2024, independent researchers analyzing globular clusters using a completely different method found ages consistent with a universe significantly older than 13.8 billion years. They explicitly mentioned Gupta's work as providing a framework that could accommodate their findings. Other teams began quietly reanalyzing archival data from Hubble and other telescopes, looking at early galaxy observations through the lens of an extended timeline. Some preliminary results suggested that things fit better than expected. The galaxies weren't as impossibly massive if they had more time to form. The scientific method doesn't progress through dramatic revelations where everyone instantly accepts a new truth. It progresses through slow accumulation of evidence through independent verification, through people checking and rechecking, until a consensus gradually emerges. Gupta himself has been careful in presenting his findings. He doesn't claim absolute certainty. He describes his model as addressing specific problems in current cosmology and offering a potential resolution worth serious consideration. In interviews, he emphasized that science advances by testing alternative ideas rather than rigidly defending the status quo. The Lambda CDM standard model works well for many observations. It's been enormously successful, but it struggled with the James Webb discoveries and ancient star ages. Rather than forcing those observations to fit the model through increasingly complex explanations, perhaps the model itself needs revision. Doubling the universe's age is admittedly radical, but so was the Big Bang when first proposed. Revolutionary ideas often seem absurd until evidence forces acceptance. Have you ever learned someone's real age and thought, there's no way? The universe is giving us exactly that feeling right now. The implications extend far beyond just fixing technical problems in cosmology. If the universe is 26.7 billion years old, the entire narrative of cosmic evolution changes. The gap between the Big Bang and the first stars lengthens. Early galaxies had more time to grow, merge, and develop complexity. The Milky Way's formation history gets rewritten with a longer, more gradual timeline. Life on Earth appearing around 4 billion years ago occupies an even tinier fraction of cosmic history than we thought. We're even more recent arrivals in an even more ancient universe. And perhaps most intriguingly, the question of what happened before the Big Bang becomes more pressing, because now there's more time to account for, more history to explain, more mystery about what conditions preceded the explosion that started everything we see. But to understand how Gupta arrived at this radical conclusion, we need to resurrect a ghost from physics past. 1929 was a remarkable year for cosmology. Edwin Hubble was discovering that the universe expands. Einstein was grappling with the implications for his equations. And a Swiss astronomer named Fritz Zwicky was thinking about light in a completely different way. Zwicky noticed the same galactic redshifts that Hubble observed. Distant galaxies appeared redder than nearby ones. Their spectral lines were shifted toward longer wavelengths. But where Hubble saw expanding space stretching light like rubber, Zwicky saw something else entirely. What if light simply gets tired? Photons travel for billions of years across the cosmic void. Maybe they lose energy along the way, gradually shifting toward the red end of the spectrum without any space expansion at all. The redshift we observe wouldn't be evidence of motion or expansion. It would just be exhausted light worn down by the journey. Zwicky called it tired light theory, and for decades it competed seriously with the Big Bang model as an explanation for cosmic redshift. The idea has intuitive appeal. Energy doesn't come from nowhere and doesn't disappear without reason. Light crossing vast cosmic distances might interact with something in the space between galaxies. Perhaps encounters with intergalactic gas particles. Perhaps gravitational interactions with matter along the way. Each interaction would be tiny, utterly negligible over short distances. But after billions of light years, the cumulative effect could produce substantial redshift. tired light offered an alternative to space expansion. The universe could be static, eternal, unchanging. Galaxies weren't flying apart in the aftermath of some primordial explosion. Their light was just losing energy as it traveled to our telescopes. For years, tired light remained viable. Some astronomers preferred it to the seemingly religious implications of the Big Bang, which suggested a moment of creation. A beginning to time itself felt more like theology than physics. But observations gradually killed the theory. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background using a radio antenna in New Jersey. This faint radiation, pervading all of space, had exactly the properties predicted by Big Bang models. It was the afterglow of creation itself, cooled by expansion from thousands of degrees to just a few degrees above absolute zero. Tired light couldn't explain it. If the universe was static and eternal, where did this radiation come from? The Big Bang provided a natural explanation. Tired light had none. The final nail came from observations of distant supernovae in the 1990s. Type Ia supernovae explode with consistent brightness, making them excellent distance markers. But astronomers noticed something crucial. Light from distant supernovae appeared not just redder, but also stretched in time. Explosions that should take weeks to brighten and fade appeared to last months when viewed from extreme distances. This time, dilation effect is predicted by expanding space. If space expands, while light travels to us, the light waves stretch, and timestamps on those waves spread out. Events appear to happen in slow motion. Tired light predicts no time dilation. Photons just lose energy. Their frequency changes, but their timing doesn't. The supernova observations matched expansion predictions perfectly and contradicted tired light completely. Tired light was declared dead. Cosmology textbooks relegated it to the historical curiosities section, mentioned only as an example of what doesn't work. It became a cautionary tale about the importance of testing theories against diverse observations. Yet Zwicky's core insight never completely disappeared. A few researchers continued exploring variations, wondering if perhaps tired light wasn't entirely wrong, just incomplete. What if both processes occur? What if redshift has two components, one from expansion and one from energy loss? That's exactly what Gupta proposed, not pure tired light, which we know doesn't work, but a hybrid model where most redshift comes from cosmic expansion, as the standard model says, but a small additional component comes from tired light effects. By allowing redshift to have two sources, he could reinterpret observations in a way that extends cosmic timelines without contradicting the key evidence that killed tired light decades ago. The mathematics works like this. Standard cosmology interprets all redshift as expansion. A galaxy with redshift factor of 10 existed when the universe was roughly 1/11th its current size. That places it very early and very far away, about 13 billion light years distant. But if half the redshift comes from tired light and half from expansion, that same galaxy isn't as distant or as early. It's somewhat closer and formed somewhat later. The tired light component makes it appear more redshifted than expansion alone would cause. The effect compounds over cosmic distances. For nearby objects, the difference is negligible. You can't tell whether redshift is pure expansion or hybrid. But for the most distant objects visible to James Webb, the difference becomes enormous. Galaxies we thought formed 500 million years after the Big Bang might have actually formed 1 or even 2 billion years later. The extra time solves the maturity problem. Star formation can proceed normally. Structures have time to develop naturally. Think of it like driving from Hanoi to Saigon. If 100% of the road is smooth highway, you arrive in 24 hours. But if 50% is smooth and 50% is rough, bumpy road that slows you down, you might take 36 to 40 hours. Same distance, different travel time. Critics immediately attacked the hybrid model. They pointed out that tired light predicts different surface brightness patterns for galaxies than expanding space does. Observations favor expansion. They noted that the cosmic microwave background's uniformity and spectrum are explained beautifully by expansion but not by tired light mechanisms. These aren't minor issues. They're fundamental tests that originally killed tired light. Gupta's response was that his model isn't pure tired light. It's a small tired light contribution layered on top of standard expansion. The expansion component handles most observations, normally including the cosmic microwave background and supernova time dilation. The tired light component just adds a correction that changes how we interpret distances and ages. Whether this actually works depends on detailed calculations and future observations. But here's what makes it compelling. Some researchers who initially dismissed the paper started reconsidering after James Webb continued finding more and more problematic galaxies. If the alternative is accepting that early universe physics was radically, inexplicably different from everything we understand, maybe reconsidering tired light isn't so crazy after all. Science has a history of resurrecting old ideas when new data demands it. Continental drift was mocked before becoming plate tectonics. Atoms were considered philosophical nonsense before quantum mechanics made them real. Black holes seemed like mathematical fantasies before we detected them. The deeper question is what physically causes tired light effects, if they exist. Zwicky never provided a satisfying mechanism. Photons don't just lose energy spontaneously for no reason. Something must cause it. Modern proposals involve interactions with quantum vacuum fluctuations, the seething activity of virtual particle pairs, appearing and vanishing in supposedly empty space. Perhaps photons exchange tiny amounts of energy with these quantum fluctuations over cosmic distances. Each interaction is infinitesimal, negligible nearby. But over billions of light years, the cumulative effect becomes substantial. Another idea involves gravitational interactions with the cosmic web, the large-scale structure of dark matter filaments and galaxy clusters. As light passes through varying gravitational fields, it might lose energy through mechanisms not fully captured by general relativity. None of these mechanisms are proven. They're speculative attempts to make tired light physically plausible. But that's how science progresses. Observations come first. Phenomena are recognized before mechanisms are understood. We observed cosmic expansion decades before understanding dark energy. We detected gravitational waves a century after Einstein predicted them. If tired light effects are real, the mechanism will eventually be found. But tired light alone isn't enough to double the universe's age. For that, Gupta needed something even more radical. 1937, Paul Dirac sat in his office at Cambridge University, one of the most brilliant minds in physics, staring at numbers that bothered him deeply. Dirac was one of the founders of quantum mechanics. He predicted the existence of antimatter before anyone had detected it. His equations describing electron behavior were so beautiful that other physicists called them poetry written in mathematics. When Dirac spoke, people listened, and what he said in 1937 sounded completely insane. What if the constants aren't constant? In physics, certain numbers appear in every equation describing reality: the speed of light, the strength of gravity, the charge of an electron. These are called fundamental constants because they're supposed to be unchanging throughout space and time. They're the fixed rules by which the universe operates. Dirac asked, what if they're not fixed? What if they change? His reasoning came from noticing strange numerical coincidences. The ratio between the strength of electromagnetic force and gravitational force is enormous, around 10 to the 40th power, 1 followed by 40 zeros. That's a stupendously large number. The age of the universe expressed in atomic time units gives a similarly huge number, also around 10 to the 40. Dirac found this suspicious. Why should two completely unrelated quantities have similar values? Maybe they weren't coincidences. Maybe the constants of nature evolve as the universe ages, maintaining these relationships over time. Specifically, he proposed that the gravitational constant might have been stronger in the early universe and gradually weakened. If true, this would mean the physics of the early cosmos operated differently than physics today. Gravity pulled harder, stars burned differently, everything worked according to slightly different rules. Most physicists ignored this idea. It seemed untestable. How do you check if constants changed billions of years ago? And it felt philosophically uncomfortable. We call them constants precisely because they shouldn't change. Allowing them to vary felt like pulling the rug out from under all of physics. But modern cosmology has given us ways to look back in time. Light from distant galaxies shows us the universe as it was billions of years ago. By studying the spectral lines in that ancient light, we can measure what the constants were when the light was emitted. Several research groups have done exactly this over the past 2 decades, looking for evidence that the fine structure constant, which governs electromagnetic interactions, might have varied over cosmic history. The results are tantalizing, but not conclusive. Some studies claim to detect tiny variations at high redshift, suggesting the constant was slightly different, billions of years ago, perhaps, by 1 part in 100,000. Other studies find no significant change within measurement uncertainties. The measurements are at the edge of what current instruments can detect. Error bars are large. The scientific community remains divided on whether variations have been proven. But the possibility remains open. The door hasn't been closed. If constants do evolve even slightly, it would transform our understanding of physics and cosmology. It would mean the laws of nature aren't eternal and unchanging. They develop over time like everything else in the universe. Gupta's model incorporates evolving coupling constants as a core component. But he doesn't just use Dirac's gravitational constant idea. He considers constants related to how light and matter interact. These coupling constants determine the strength of interactions between photons and atoms. If these constants were different in the early universe, photons would behave differently. The rate at which atoms absorb and emit light would change. This affects how we interpret observations of distant galaxies. Light we receive from the early universe might carry signatures of different physics, and we've been misinterpreting those signatures by assuming constants never change. The mathematics involved gets technical fast. Coupling constants appear in quantum field theory. Equations describing particle interactions change the constant and interaction rates change. This affects stellar evolution, nuclear fusion rates, even the formation of atoms in the early universe after the Big Bang. Small changes to constants can have cascading effects through all of physics. It's like changing the rules of a game slightly. The game still functions, but strategies that worked before might not work anymore. Outcomes change in subtle but significant ways. Gupta showed that by allowing specific coupling constants to evolve according to particular mathematical functions, he could extend the timeline of cosmic history while still matching observations of the cosmic microwave background and galaxy distributions. Critics point out that evolving constants create their own problems. If the strength of electromagnetic force changed over time, the fusion reactions inside stars would have operated differently in the past. This would affect the abundance of light elements like hydrogen, helium, and lithium produced in the Big Bang and in early stars. We measure those abundances in ancient gas clouds that have never formed stars, pristine material left over from the cosmic dawn. They match predictions assuming constant constants very well. Changing the constants to solve one problem risks creating mismatches in element abundances. Gupta's model needs to carefully tune how constants evolve to avoid these issues. The tuning has to be precise. Too much change, and you break things that currently work. Too little, and you don't solve the age problem. Another concern involves fundamental physics theories. Constants aren't arbitrary numbers someone made up. They emerge from the underlying structure of quantum field theory and general relativity. Changing them requires understanding why they change and what mechanism drives the evolution. String theory, one approach to unifying quantum mechanics, and gravity actually predicts that constants could vary if extra dimensions of space change size over cosmic time. But string theory itself remains unproven and controversial, with no experimental confirmation yet. Basing a cosmological model on speculative physics makes many scientists uncomfortable. It's like building a house on land that might not exist. Yet the coupling constants idea has a crucial advantage. It provides a physical mechanism for why the universe could be older than standard models suggest. It's not just saying the universe is older without explanation. It's explaining how that extra time is consistent with observations that seem to constrain the age tightly. By allowing physics itself to evolve, the model creates wiggle room in the timeline. Processes that we think took a certain amount of time based on today's physics might have taken longer when constants were different. Galaxy formation stellar evolution, element creation, all could have operated on extended timescales in the early universe without violating any observations we can make today. And right now you might be thinking, this story is getting more complicated. That's true, because the truth is rarely simple. But stay with me. The final pieces are coming together. Testing this requires observations that are just becoming possible with James Webb and future instruments. By measuring the spectra of early galaxies, precisely astronomers can look for anomalies that might indicate different coupling constants operating in the distant past. If the fine structure constant was different spectral lines would appear shifted in specific ways compared to predictions. If stellar evolution constants varied stars in early galaxies would have different colors, temperatures, and lifetimes than models predict based on current constants. The data is starting to come in. So far, no smoking gun has appeared, no definitive proof that constants evolve. But the search continues, because if constants do change with cosmic time, it would be one of the biggest discoveries in physics. It would mean that time doesn't just measure duration, it measures transformation. The universe doesn't just get older, it gets different. Physics at the beginning wasn't the same as physics now. The rules themselves have a history. Maybe you've thought to yourself before, if only I had more time. The universe is the same. If physics gives it more time, everything impossible suddenly becomes possible. And when you apply this framework to all the observations that seemed broken, something remarkable happens. Let's go back through everything that seemed wrong and see what happens when you apply Gupta's framework. When you combine tired light effects with evolving coupling constants and extend the cosmic timeline to 26.7 billion years, it's like putting on glasses for the first time and realizing the world has sharp edges. Start with the James Webb galaxies, those 6 bright red dots and dozens of others found since. Massive structures containing tens of billions of stars existing supposedly just 5 to 700 million years after the Big Bang. In the standard timeline, this is impossible. The mathematics doesn't work. Star formation can't proceed fast enough. Feedback processes should prevent such rapid growth. But in Gupta's framework, those galaxies didn't form 5 to 700 million years after the beginning. The redshift we measure includes both expansion and tired light components. When you separate them, the galaxies formed between 1 and 2 billion years after the actual beginning. Suddenly everything changes. 1 to 2 billion years is plenty of time for normal star formation processes. You don't need hundreds of stars forming per year. You need 50 to 100 sustained over longer periods. That's high, but not physically impossible. Efficiency doesn't need to violate the 20% limit. It can be 30 or 35% elevated, but not absurd. Feedback processes operate normally. Gas gets heated by supernova and stellar winds temporarily halting star formation, then cools and resumes. The cycle repeats over 1 billion years instead of half that. Structures have time to develop naturally through gravitational interactions and mergers. Disk formations make sense. Spiral patterns emerge gradually. The galaxies look mature because they are mature. They've had twice as long to evolve as we thought. Problem solved. Not through exotic physics, not through special conditions, just through having more time. Move to Methuselah and the ancient stars. Of 14 to 16 billion year old star was older than a 13.8 billion year old universe. That's a paradox. An object can't exist before its container. But 14 billion years isn't older than 26.7 billion years. Suddenly, Methuselah isn't a paradox. It's just an ancient star that formed relatively early, perhaps 5 or 6 billion years after the actual beginning of everything. That's still early. The star is genuinely old, but it's not impossible anymore. Error bars don't need to be manipulated to barely overlap with the universe's age. The measurements stand as they are. The star is 14 billion years old, give or take. The universe is 26 billion years old, give or take. No contradiction. Globular clusters throughout the Milky Way's halo, showing ages of 12 to 13.5 billion years, also stop being problematic. Instead of forming just 3 to 800 million years after the Big Bang, an impossibly tight timeline, they formed 2 to 3 billion years afterward. That's approximately halfway through cosmic history in the extended timeline. Plenty of time for the first generation of stars to form from primordial gas, live their lives, die as supernovae, and enrich space with heavy elements. Plenty of time for the second generation to coalesce into dense clusters. The formation process proceeds at a normal, unhurried pace. The Hubble tension, that troubling disagreement between different methods of measuring cosmic expansion, eases considerably. With a longer timeline, there's more flexibility for expansion rates to vary over cosmic epochs in ways that reconcile nearby measurements with cosmic microwave background predictions. The tension doesn't disappear completely. There's still work to be done, but it's no longer a crisis threatening the foundation of cosmology. It becomes a refinement problem rather than a fundamental breakdown. In 2024, independent confirmation emerged from an unexpected direction. Researchers using a completely different technique called the blue straggler method found ages for globular clusters consistent with a significantly older universe. Blue stragglers are unusual stars in ancient clusters that appear younger and bluer than their neighbors thought to form through stellar collisions or mass transfer between binary stars. The distribution and properties of blue stragglers provide an independent age estimate that doesn't rely on stellar evolution models. When this team applied their method to several clusters and published their results, they explicitly stated their findings support the idea that the universe may be older than standard models indicate. They pointed to Gupta's work as offering a framework that could accommodate their measurements. Multiple teams around the world began quietly reanalyzing archival data from Hubble and other telescopes, looking at early galaxy observations through the lens of an extended timeline. Some preliminary results came back with phrases like consistent with extended timeline and better fit than standard model. These aren't definitive confirmations. Science doesn't work through dramatic announcements where everyone instantly accepts a new paradigm. But the evidence is accumulating, slowly, carefully, the way good science always does. It's like when you dump out a jigsaw puzzle, frustrated because the pieces won't fit. Then someone points out the box says 500 pieces, but actually contains 1,000. Suddenly everything makes sense. The pieces still don't fit easily. You still have to work at it. But at least you're not trying to force them into impossible configurations anymore. Metal enrichment history also relaxes into something physically reasonable. The universe started with only hydrogen helium and trace lithium. Everything heavier had to be created inside stars over multiple generations. This chemical evolution takes time. In 13.8 billion years, you need multiple stellar generations, forming and dying in rapid succession within the first billion years. It's possible, barely, but it requires everything to happen with ruthless efficiency. In 26 billion years, chemical enrichment proceeds gradually. The first generation of massive stars forms lives briefly and dies within a few 100 million years. Their supernovae scatter heavy elements. The second generation forms from enriched gas over the next billion years. Some of those stars die further, enriching space. The third generation, including stars like Methuselah, forms from gas now containing enough metals to cool efficiently and form planets. The process is natural, unhurried, physically plausible. No special conditions required, just normal stellar evolution given to adequate time. But if this framework is correct, it doesn't just change the timeline, it changes what came before the beginning itself. There's one observation that stands above all others in cosmology, one measurement so precise, so fundamental, that any alternative theory must explain it or die trying. The cosmic microwave background. 380,000 years after the Big Bang, something extraordinary happened. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, space was opaque, filled with a hot plasma of charged particles that scattered light in every direction, like fog scattering headlight beams. After, atoms formed photons could travel freely. Light was released from the cosmic fog and began its journey across space. That light has been traveling ever since, stretched by billions of years of cosmic expansion from visible wavelengths into microwaves. This cosmic microwave background, discovered in 1964, is the oldest light we can see. It's the baby picture of the universe, and it's stunningly uniforms. Look in any direction in space, and you'll measure microwave radiation at the same temperature, 2.7 degrees, above absolute zero, with variations of only 1 part in 100,000. The European Planck satellite mapped these tiny temperature fluctuations with exquisite precision. The pattern encodes information about the universe's composition, geometry, age, and fate. By fitting theoretical models to this pattern, cosmologists derived the 13.797 billion year age with less than 1% uncertainty. The cosmic microwave background is cosmology's gold standard, the observation that most tightly constrains models. Any theory claiming the universe is older must explain why the CMB looks exactly as it does. This is Gupta's biggest challenge. The interpretation of CMB data depends on assumptions about physics during the era when atoms formed, the rate at which electrons and protons combined, the opacity of the plasma before recombination, the speed at which sound waves traveled through the primordial gas. All these processes depend on fundamental constants governing how light and matter interact. If those constants were different, as Gupta proposes, the processes occurred differently. What looks like a universe 13.8 billion years old, under the assumption of constant constants, might actually be a universe 26 billion years old, with evolving constants. The same observations could fit either scenario with appropriate parameter adjustments. This creates a genuine problem. Critics emphasize that adding free parameters like time-varying constants allows fitting almost any data. The model risks becoming unfalsifiable, capable of explaining anything, and therefore explaining nothing. It's like adding epicycles to planetary orbits in ancient astronomy. You can always make the model fit observations by adding more complexity, but that doesn't mean the model reflects reality. For an older universe model to be scientifically useful, it must make specific testable predictions that differ from standard cosmology. It can't just say, we can fit the CMB with different parameters. It needs to predict something new that we can observe and check. One potential test involves the scale of CMB fluctuations. Inflation theory, which describes the exponential expansion in the universe's first fraction of a second, predicts that fluctuations should appear on scales larger than the cosmic horizon at recombination time. These super-horizon fluctuations are a key signature that inflation occurred. Standard cosmology sees these clearly in CMB data. If the universe is twice as old, the horizon scale calculation changes. Super-horizon fluctuations might appear at different angular scales on the sky. Future CMB experiments with higher resolution and sensitivity could potentially distinguish between standard and extended timeline models by precisely measuring these scales. Another avenue involves subtle anomalies in the CMB that don't fit the standard lambda CDM model perfectly. There's a large cold spot, a region with lower than expected temperature. The distribution of fluctuations on large angular scales shows slight deviations from predictions. These anomalies are at low statistical significance. They might be random fluctuations, cosmic variance. That means nothing, but they've persisted through multiple independent analyses using different methods. Some cosmologists wonder if they hint at new physics. An older universe with different early expansion history might naturally explain these anomalies, or they might still be nothing. The data isn't conclusive either way. What is clear is that the CMB remains the most important constraint on any alternative cosmology. Gupta's work attempts to reproduce CMB observations by carefully balancing the tired light component evolving constants and standard expansion. Whether this succeeds requires expert analysis beyond simple claims. Multiple research groups are currently studying whether his approach genuinely fits all CMB observations or whether hidden inconsistencies lurk in the details. The CMB has demolished many alternative cosmologies over the decades. It might demolish the older universe idea too, or it might, with sufficiently careful analysis, become evidence supporting it. The jury is still out. Now consider dark matter and structure formation. 85% of the universe's matter is invisible. It doesn't emit light. It doesn't absorb light. It interacts only through gravity. We know it exists because we see its gravitational effects everywhere. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than all their stars and gas combined. Gravitational lensing bends light in ways requiring additional unseen mass. Dark matter permeates the universe. Its gravity shaped every structure we see. In standard cosmology, dark matter clumped together first after the Big Bang. Tiny quantum fluctuations in a dark matter density got amplified by cosmic expansion. Denser regions had stronger gravity, pulling in more dark matter. Over millions of years, these density peaks grew into massive halos. Regular matter, hydrogen, and helium gas fell into these dark matter wells. The gas cooled, fragmented, and formed the first stars and galaxies. This process is hierarchical. Small structures form first. They merge into larger structures over time. The Milky Way built up through hundreds of mergers of smaller galaxies across billions of years. It's slow, gradual, inexorable. The key word is time. Hierarchical structure formation has minimum timescales, determined by orbital dynamics and gravitational interaction rates. You can't rush it. Dark matter interactions are weak. Halos grow at the pace. Gravity allows no faster. In simulations starting from a 13.8 billion-year-old Big Bang, the first galaxies don't appear until around 200 million years later. They're small, containing perhaps 10 million stars. By 500 million years, you might have galaxies with 100 million stars if everything goes perfectly. Structures as large as the Milky Way take 10 billion years or more to assemble. James Webb found massive galaxies at 500 million years containing billions of stars. This breaks the hierarchical timeline. Either structure formation was radically accelerated or the universe had more time. Acceleration is hard to explain. You can't make dark matter clump faster without changing its fundamental properties. Some theorists proposed that dark matter in the early universe was warmer or more interactive, allowing faster clumping. But these modifications create problems matching other observations. An extended timeline resolves this naturally. If cosmic dawn occurred 2 billion years after the beginning, instead of 500 million, dark matter halos had 3 to 4 times longer to grow. Hierarchical formation proceeds at its normal, slow pace. Mergers happen gradually. The massive galaxies observed by Webb had sufficient time to reach their observed masses through conventional physics. No exotic dark matter properties needed. No accelerated formation mechanisms required. Just standard structure formation with more time to work. Dark matter does exactly what we expect it to do. It just had longer to do it. The simplicity is compelling. One change doubling the age, and multiple independent problems ease simultaneously. That's not coincidence. That's evidence the change might be correct. But let's be honest about the situation. Gupta's model is not consensus. Most cosmologists remain committed to the standard 13.8 billion year timeline. The Lambda CDM model works well for the vast majority of observations. Overturning it requires overwhelming evidence, not just intriguing hints. More observations are needed. James Webb will continue studying early galaxies with increasing precision. Future telescopes will probe even deeper into cosmic history. Detailed spectroscopy will reveal whether early galaxies truly show signatures of different physics or just need more time. More modeling is needed. Gupta's framework is just a starting point. Other researchers need to test it, challenge it, refine it, or demolish it through rigorous analysis. That's how science progresses. Ideas compete, evidence decides. The older universe model might be wrong. It might fade into obscurity, like countless other alternative theories. Or it might, through slow accumulation of supporting evidence, gradually shift from fringe idea to serious contender to new paradigm. We don't know yet, and that's okay. Science isn't about certainty. It's about following evidence wherever it leads, even when it leads somewhere uncomfortable. Tonight, as you prepare for sleep, remember this science isn't about being sure. It's about being willing to change when evidence demands it. And the evidence is accumulating, slowly, carefully, but undeniably. If the universe truly is twice as old as we thought, that changes everything. But it also raises the most profound question of all. What came before the Big Bang itself? For decades, cosmologists spoke of the Big Bang as the absolute beginning. Time itself started in that fireball 13.8 billion years ago. Space began expanding from a singularity of infinite density. Before that moment, there was nothing. No space, no time, no matter, no energy, just nothing. Asking what came before the Big Bang was considered meaningless, like asking what's north of the North Pole. The question doesn't make sense, because before requires time, and time didn't exist before the beginning. That's what we taught in every physics class. That's what every documentary explained. The Big Bang was ground zero, the ultimate origin story. Then in the early 1980s, a physicist named Alan Guth had an idea that changed everything. What if the Big Bang wasn't the beginning? What if something came before it? Guth proposed cosmic inflation, a period of exponential expansion that occurred before the hot, dense Big Bang we know. This wasn't a minor tweak to existing theory. It was a fundamental reconceptualization of cosmic history. The Big Bang wasn't creation itself. It was a transition from one state to another. Here's how inflation works. Imagine the universe at 10 to the negative 36th seconds after time began. That's a decimal point, followed by 35 zeros, and then a 1, an incomprehensibly tiny fraction of a second. At this moment, the universe is unimaginably small, perhaps the size of a proton, but it's already smooth and uniform because it's so tiny that light has had time to travel across it. Everything is in thermal equilibrium. The temperature is the same everywhere. Suddenly, a strange form of energy permeating empty space itself drives exponential expansion. This energy comes from a field called the inflaton. We don't know exactly what it is. We've never detected it directly, but the mathematics required something like it. The universe doubles in size, then doubles again, and again, and again, at least 80 times in less than a trillionth of a second. Each doubling takes almost no time at all. The expansion is so fast, it dwarfs the speed of light. But that's okay. Nothing is moving through space faster than light. Space itself is expanding. That's allowed. General relativity permits space to grow at any rate. The speed limit applies to things moving through space, not to space itself. After inflation ends, the inflaton field's energy converts into ordinary particles and radiation. This conversion floods space with matter and energy, creating the hot, dense conditions we call the Big Bang, the fireball, the explosion, the dramatic beginning, everything we traditionally call the Big Bang, the formation of particles, the synthesis of light elements, the cooling and expansion, all of that happens after inflation stops. The Big Bang is the aftermath of inflation, not the beginning of everything. Think of it like inflating a balloon. Initially, it's tiny, almost impossible to blow up. You pump hard a few times, and suddenly it expands rapidly. That's inflation. Then you let go, and air slowly escapes. That's cosmic expansion after the Big Bang. The Big Bang is the hissing sound when you release your grip, not the moment you started pumping. This completely changes the conceptual framework. Time extends before the hot Big Bang to the inflationary era. And if time extends backward through inflation, maybe it extends even further beyond that. The implications are staggering. If inflation happened, the observable universe is just a tiny patch of a vastly larger space. During inflation, our patch was stretched to cosmic scale, but other patches underwent the same process elsewhere. The total space might be infinite, filled with countless regions like ours, each experiencing its own Big Bang when inflation ended locally. This leads naturally to the multiverse concept, which we'll explore shortly. But first understand why inflation is necessary. Why did physicists invent this seemingly bizarre idea? 3 major problems plagued Big Bang theory without inflation. First, the horizon problem. The cosmic microwave background shows that distant regions of the universe, regions separated by such vast distances that light hasn't had time to travel between them, somehow have identical temperatures. How did they equalize if they've never been in contact? Without inflation, there's no answer. Inflation solves this. Before expansion, the entire observable universe was tiny enough that light could travel across it. Everything reached thermal equilibrium. Then inflation stretched this small, uniform region to cosmic scales. That's why distant regions have the same temperature. They started in contact, then were pulled apart. Second, the flatness problem. The geometry of the universe appears almost perfectly flat. Parallel lines stay parallel. The angles of triangles add to 180 degrees. But this requires incredibly fine-tuned initial conditions. Deviation from flatness grows over time. For the universe to be nearly flat today, it had to be extraordinarily flat at the beginning. Why inflation solves this too. Any curved surface becomes flat if you expand it enough. Inflate a wrinkled balloon and the wrinkles smooth out. Inflate the universe by a factor of 10 to the 80 or more, and any initial curvature gets stretched to undetectable flatness. Third, the monopole problem. Grand unified theories of particle physics predict exotic magnetic monopoles should have been produced in huge numbers in the early universe. We've never found a single one. Where are they? Inflation dilutes them. If monopoles formed before inflation, the exponential expansion would spread them so thin that finding one would be essentially impossible. They still exist, just vanishingly rare. 3 problems, 1 solution. That's the mark of a good theory. Evidence for inflation comes from the cosmic microwave background. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating the density variations we see as temperature fluctuations in the CMB. The pattern of these fluctuations matches inflation predictions remarkably well. Inflation also predicts a nearly flat universe geometry, which observations confirm, and it predicts a specific type of fluctuation spectrum called nearly scale invariant, which is exactly what we observe. No alternative theory explains all these observations as simply as inflation does. That's why it's become the standard paradigm accepted by the vast majority of cosmologists, despite the fact that we still don't fully understand what drives it. And if you're comfortable with the idea that something existed before the Big Bang through inflation, then accepting even more time before, that starts feeling less crazy. But inflation opens doors to ideas even stranger than an older universe. Inflation solves the problems of Big Bang cosmology beautifully, but it creates something even more profound, something that changes our understanding of existence itself. Inflation doesn't end everywhere at once. Think about it. Inflation is driven by a quantum field, and quantum fields fluctuate randomly. In some regions, the field decays quickly, and inflation stops. Those regions transition to a hot Big Bang. But in other regions, quantum fluctuations keep the field energized. Inflation continues there. This creates a fractal structure. Some patches stop inflating and become universe bubbles, like ours. But between those bubbles, space continues inflating exponentially, constantly generating more volume that spawns more bubbles. The process never ends. It's eternal to the future. And according to some models, it's eternal to the past as well. There was no beginning. Inflation has been happening forever, continuously creating bubble universes. Our observable universe is one bubble in an infinite cosmic foam. Each bubble universe exists beyond the cosmic horizon of every other bubble. The space between bubbles expands faster than light travels, ensuring that different bubbles can never interact or communicate. We're forever isolated in our bubble, unable to see or reach the others. But here's where it gets truly strange. Each bubble universe might have different physical properties. The strength of fundamental forces, the masses of particles, even the number of spatial dimensions could vary from bubble to bubble. These properties are determined by how the inflaton field decays when inflation ends locally. Random quantum fluctuations during inflation could set different physical constants in different bubbles. Most variations would produce lifeless universes with physics incompatible with structure formation. No stars, no galaxies, no chemistry, no life. We find ourselves in a rare bubble where constants permit complexity. Stars can form, heavy elements can be created, planets can exist, life can emerge. This is called anthropic reasoning. The universe isn't fine-tuned by design. It's randomly selected from infinite possibilities. And observers can only exist in bubbles where existence is possible. We're here because we have to be somewhere, and this is one of the somewheres that works. The multiverse isn't speculation or philosophy. It's a prediction that emerges naturally from inflation theory, combined with our understanding of quantum fields. If inflation happened, and the evidence suggests it did, then eternal inflation and bubble universes follow almost inevitably from the mathematics. String theory, a leading candidate for unifying quantum mechanics and gravity, strengthens the case. String theory predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws. The number of possibilities is enormous, perhaps 10 to the 500th power or more. Each bubble universe in eternal inflation could realize a different vacuum state from the string theory landscape. This connects quantum gravity to cosmology in a deep way. The multiverse becomes the natural arena where string theory operates. Single universe models start looking special and unlikely. Now consider what an older universe means for the multiverse picture. If our bubble formed 26.7 billion years ago, rather than 13.8, our position in the eternal inflation process shifts. We're older relative to other bubbles. The statistical distribution of bubble ages throughout the multiverse depends on details of how inflation proceeds. If some mechanism favors longer-lasting inflation before bubbles nucleate, the typical bubble might be older than standard models predict. Our bubble's age would reflect this preference. Finding that we're older than expected might be evidence for specific inflation models over others. There's also a technical issue called the measure problem in eternal inflation. This asks how to calculate probabilities in an infinite multiverse. If infinitely many bubbles exist, and infinitely many contain observers like us, how do we determine what's typical versus rare? Different approaches to this problem, called measures, predict different age distributions for observer-bearing bubbles. Observational data about our universe's age, structure, and properties constrain which measures work. An older universe might favor certain measures over others, helping narrow down theories. String theory's landscape of 10 to the 500th power vacuum states means that somewhere in the multiverse, every possibility is realized. Bubbles, where gravity is stronger. Bubbles, where electrons are heavier. Bubbles, where there are 5 spatial dimensions instead of 3. Our older age constrains which vacuum states are actually realized and how frequently. It's a clue about the underlying probability distribution across the landscape. So you're not special. Your universe isn't special. But don't feel bad. There are infinite versions of you in infinite other universes feeling equally unspecial right now. And this is where our story becomes slightly terrifying. Because if what we're saying is true, then everything is vastly larger than we imagined. Not everyone accepts the multiverse. Critics argue it's untestable and therefore not science. If other universes are forever beyond observation, how can we ever prove they exist? Defenders respond that many accepted scientific theories involve unobservable entities. We can't directly see electrons. The interior of black holes is hidden from view. We infer their existence from observable effects. Similarly, we might infer the multiverse from observations like the universe's age, the values of constants, and the properties of the cosmic microwave background. The multiverse makes predictions about what we should observe in our bubble. An older universe strengthens some multiverse models and weakens others. Models that predict young bubble universes struggle if ours is actually old. Models that allow wide age variation accommodate the finding easily. As James Webb and future instruments refine our knowledge of cosmic history, they're not just telling us about our universe, they're constraining theories about the much larger multiverse structure our universe might inhabit. But the multiverse isn't the only way to think about what came before our Big Bang. What if the Big Bang wasn't the first? What if our universe's beginning was actually a bounce from a previous universe that had collapsed? This is the cyclic universe model, and it offers a completely different perspective on cosmic history, one that's somehow both humbling and awe-inspiring. In this framework, the Big Bang we know wasn't creation, it was a transition. The previous universe had expanded for billions or trillions of years, then reversed course and began contracting. All the matter and energy collapsed back together in a big crunch, the opposite of the Big Bang. But instead of collapsing to infinite density and ending in a singularity, something happens at extreme density, a bounce, quantum gravity effects, or exotic physics we don't fully understand prevent the collapse from reaching zero size. The universe rebounds, exploding outward in what we perceive as our Big Bang. Then the cycle repeats. Bang expansion, eventual contraction, crunch, bounce, bang again, over and over, extending infinitely into the past and future. No beginning, no end, just eternal cycling. If each cycle lasts approximately 26 billion years, we're currently somewhere in the middle of our cycle, perhaps halfway through, before gravity eventually halts expansion and begins pulling everything back together billions of years from now. Before our Big Bang, there was a previous universe with its own history. Galaxies formed and died. Stars were born and exploded. Perhaps even civilizations rose and fell. Then that universe contracted and bounced into ours. Before that universe was another one, and before that another, extending backward through infinite cycles. Time doesn't begin, it's eternal. Creation myths from human cultures might be metaphorical rather than literal. Existence has always been and always will be. We're just one iteration in an endless sequence. It's like seasons. Spring doesn't begin existing for the first time. It returns, departs, then returns again. The universe might operate exactly the same way. The philosophical implications are profound. If time is eternal, questions about ultimate origins become meaningless. There is no first cause because there's no first moment. Every cycle is caused by the previous cycle. The chain extends backward forever. Some people find this disturbing. It removes the possibility of a moment of creation. Others find it beautiful. Existence is eternal and indestructible. The universe can never truly end because every crunch leads to another bounce. Cyclic models face significant challenges. What causes the bounce? What prevents collapse to a singularity? We don't have proven physics for this. String theory and loop quantum gravity offer possibilities, but nothing definitive yet. Another issue involves entropy, the measure of disorder. The second law of thermodynamics says entropy always increases. In a cyclic universe, cycling forever, entropy should increase without bound over infinite cycles. Eventually, everything should reach thermal equilibrium, a heat death where nothing interesting can happen. Why hasn't that happened already if there have been infinite past cycles? Some cyclic models address this by proposing that each cycle generates fresh, low entropy matter through the bounce process. Information and entropy from the previous cycle don't completely transfer. Each cycle is partly a fresh start, which leads to something intriguing. Some versions of cyclic models predict that information from previous universes might leak into the current universe. Not complete information, just fragments, echoes from before. These echoes might appear as subtle anomalies in the cosmic microwave background. Remember those slight deviations from standard predictions we mentioned: the large cold spot, the unexpected distribution of fluctuations at large scales. Perhaps they're not measurement errors or random fluctuations. Perhaps they're memories from the universe that came before ours, faint signals that survived the bounce encoding information about conditions in the previous cycle. Testing this requires incredibly precise measurements of the CMB with future instruments more sensitive than Planck. We're looking for patterns that shouldn't be there. If our universe emerged from pristine random initial conditions, patterns that might tell stories about what came before. If verified, it would be one of the most profound discoveries imaginable. Direct empirical evidence of a universe that existed before ours. Proof that the Big Bang wasn't the beginning, but a transition. Whether cyclic models are correct remains unknown. Their minority views in cosmology, less developed than inflation-based multiverse theories, but they offer testable predictions, making them legitimate science rather than pure speculation. And here's what connects to our main story. If the universe is 26.7 billion years old, that's roughly what you'd expect for one cycle in certain cyclic models. We're in the middle expansion phase, with billions of years remaining before contraction begins. An older universe fits naturally into cyclic frameworks. It provides time for the expansion phase to develop complexity, for structures to form, for life to emerge, all before the eventual turnaround. The universe's true age doesn't just tell us when things started, it tells us about the nature of time itself. Let's pause and consider what it would mean if the universe truly is 26.7 billion years old instead of 13.8. The implications cascade through every field of science and reshape how we understand our place in existence. For physics, it means the fundamental constants we thought were eternal might actually evolve over cosmic time. The strength of forces, the masses of particles, the relationships between energy and matter could all shift gradually as the universe ages. Physics in the early universe operated under slightly different rules than physics today. This opens extraordinary possibilities. Dark energy, that mysterious force accelerating cosmic expansion, might not be constant. It could strengthen or weaken over billions of years. We've assumed it's unchanging because we've only observed it over relatively recent cosmic history. But if the timeline extends much further back, dark energy's behavior over the full span might tell a different story. Gravitational waves offer another frontier. These ripples in space-time from violent cosmic events travel at light speed across the universe. Detectors like LIGO have found waves from merging black holes and neutron stars. Future detectors might be sensitive enough to catch gravitational waves from before the Big Bang itself, from the inflationary epoch, or even from a previous cosmic cycle. Those waves would carry information about conditions before our universe began. For astronomy, every timeline needs revision. Galaxy formation, histories get rewritten. The Milky Way's assembly through mergers happened over 26 billion years, not 13. Early galaxies had twice as long to develop. The first stars formed earlier in absolute time, though later relative to the beginning. Every redshift to age conversion must be recalibrated. Astronomers will need to reanalyze decades of archival data from Hubble and other telescopes, reinterpreting observations through the lens of an extended timeline. Discoveries that seemed impossible might become normal. Anomalies might disappear. The entire history of the universe needs revision, not just tweaking, complete reconstruction. For philosophy, the implications cut even deeper. Beginning doesn't mean what we thought. Time isn't a simple arrow from creation to now. It's longer, stranger, more complex. Maybe there was no beginning at all. Maybe time extends eternally backward through infinite cycles, or through eternal inflation, generating endless bubbles, our place in the cosmos becomes even smaller in the grander scheme. We're not just recent arrivals in a 13.8 billion year old universe. We're incredibly recent arrivals in a universe twice that age, or potentially eternal. Life on Earth spanning 4 billion years seems even more fleeting against 26 billion years of cosmic history. But there's a counterbalancing perspective. If the multiverse is real, if eternal inflation generates infinite bubble universes, then existence is far more abundant than we imagined. Consciousness isn't rare. It's inevitable, arising countless times across infinite space in bubbles, where conditions permit complexity. For humanity, practically speaking, every textbook needs rewriting, every documentary needs remaking, every planetarium show explaining cosmic history requires updates. Students learning cosmology today might be learning a framework that will be obsolete within a decade. But that's how science works. Knowledge is always provisional. We build the best models we can with available evidence, knowing future discoveries might overturn everything. That's not a weakness. That's the strength of science. It updates. It corrects itself. It improves. You know that feeling when you realize your parents don't know everything? The universe just gave humanity exactly that feeling. And that's not a bad thing. It's a sign we're growing up. Science isn't about having all the answers. It's about asking better questions. And right now, the universe is teaching us that we've been asking questions with the wrong assumptions about time itself. But where does this leave us? What happens next? Here's where we stand today. Gupta's model has been published in a respected journal. It's being debated in conferences and studied by researchers worldwide. But it's not consensus. Most cosmologists remain committed to the standard 13.8 billion year timeline. The Lambda CDM model works too well for too many observations to abandon it without overwhelming evidence. James Webb continues finding more massive, mature galaxies in the early universe. Each discovery adds weight to the timeline problem. Independent teams are testing Gupta's predictions, looking for signatures in data that would distinguish between standard and extended timelines. The next 5 to 10 years will be critical. Several tests are coming that could support or demolish the older universe hypothesis. Higher resolution experiments will map the cosmic microwave background with unprecedented precision, searching for subtle patterns that reveal whether constants evolved or whether information leaked from a previous cosmic cycle. More detailed spectroscopy of high redshift galaxies will measure their properties with accuracy impossible before Webb. We'll see whether they truly show signatures of extended formation times or whether some other explanation accounts for their maturity. Gravitational wave detectors are becoming more sensitive. Future instruments might detect signals from the inflationary epoch, or even from before the Big Bang. Those detections would revolutionize our understanding of what came before. Precision measurements of how constants vary with distance and cosmic time will continue improving. If we definitively detect variation, it would validate a key component of Gupta's framework. If the older universe model is correct, we're witnessing the largest paradigm shift since Copernicus moved Earth from the center of everything. the age of everything would be doubled. Physics textbooks would be rewritten. Our understanding of time itself would be transformed. But if it's wrong, we still learn something valuable. The Standard Model has genuine problems that need solving. The massive early galaxies are real. The Hubble tension is real. Methuselah's age is real. Even if doubling the universe's age isn't the solution, something needs to change. The search continues. That's the nature of science. Not certainty, just the best explanation, given current evidence, always subject to revision when better evidence emerges. A physicist once said something profound: the universe doesn't care what we think. It just is. Our job is to listen carefully to what it's telling us. And right now, the universe is whispering, "I'm older than you thought, much older, and what came before me is stranger than you can imagine." So, next time someone asks your age, remember, even the universe is still deciding whether to reveal its true age. And tonight, when you lay down in darkness, know that the darkness has existed longer, deeper, and more mysteriously than we ever believed. Perhaps that's not frightening. Perhaps it's just a reminder that there's so much more to discover. And we've only just begun. 26.7 billion years. Maybe, or maybe not. But the fact that we dare to ask the question, that's what makes us human.